Hey everybody, we're going to go over the Dev GenAI workshop setup so that when you run this for your customers, you get as quick and smooth a setup process as possible. There's lots of links floating around. You'll have all the links should continue to work, but the main slides are here, right? And inside the slides, you'll have these yellow boxes that tell you what you need to modify in the slides and remind you to make a copy of them. But the second slide has all the links to all the instructions and the setup tool and all of that. So everything you should need should be in the slides and should be a lot simpler than how we ran it in Wave 1. So in these instruction slides, you get the step-by-step of what you need to do, what spreadsheet you need to track it in, how you need to work with marketing, where the slides are, remind you to make a copy of the slides, please. Please don't modify the template with stuff about your customer. And then how to use the setup tool. So when you're ready to use the setup tool to create your keys, right after you've gone and made your copy of the deck and you're going to make your kind of secret word of the day key and copy and paste it into there, let me show you how to use the setup tool. So you're going to use the link to get to the setup tool, and it looks like this, right? The workshop setup tool. So you're going to pick which version of the workshop that you want to run. You're probably going to be running Wave2 Colab. That's the good default. There may be other ones in there, for specialized environments later. Feel free to play with those, but most people are going to be running this Google Colab version, using kind of the environment that keeps it basic. So you're going to type in your name of your customer, your workshop name, like a short ID for it, because that's what you're going to find it by when you look for that key later. And then you're going to type in either today's date or the workshop date, which is probably, just like tomorrow, right? So I always put in today's date. I set it up the day of or the day before, and I run a little test. And once I hit go, I'm going to pull up one that I had set up for today. Here, I'm going to find, the workshop materials links that it creates for me, including the secret word of the day for the class so they can type in a key. And that's, for this case, it's wheat trial. And I'm going to go and I'm going to make a modified version of the deck where I use that special key. And it's all that my classroom will need to remember. It has a link to the actual Google Colab for Wave 2, but the slides already have that embedded in it. And I've got links to all the various dashboards that I might want to have available to kind of track my classroom, or the LLM cost dashboard, which we're going to use in the very last module to show people the results of the last lab and how many tokens that they used. So this is my modified version of the slide deck that I've got going for a workshop that I'm running today that's going to use that workshop key of wheat trial, I believe. And I've taken out some of the yellow things because, of course, I made a copy of it for my internal run of the workshop. And where, I got prompted to go and edit the deck, I went and entered my workshop key, wheat trial, right? And I've got that there so that I can have this up for my classroom to know this is the link that you need and this is the workshop key that you need. The way the workshop key works is this. So I'm going to copy it right here. I'm going to jump into this short link that my users are going to have to type in as they're following along on their laptops, because sometimes sending links through Zoom can be problematic. But I'm going to tell them to open up a specific notebook here. Say, let's imagine we're launching Lab 1. So I'm going to open up the Colab for Lab 1, and it's connecting to the environment. And I'm going to run, as it prompts me and says, hey, this wasn't authored by Google. That's cool. It was authored by, Elastic. And it is going to go and download this little environment loader that we wrote. So all they'll have to type in is that wheat trial key. So I type in wheat trial, I hit load, right? Your workshop key will be different, obviously, different magic word of the day for every classroom. And I've successfully loaded the environment variables. If you want to know what they are, they're in here somewhere. I guess they're loaded as variables into the environment. There's a way to get to them. I might have to, do a dump of the environment variables with bash or something in order to see them. I don't need to do that. But these read-only keys, these keys that do expire, are now loaded, and the class doesn't have to worry about them or deal with them. They'll all be loaded as we run through the labs. All right, so that's all you have to do to set up and get it going. And we'll show you using them when we do an actual recording, and we'll see you in the next video. Cool. Thanks, everybody. So What we're going to do is we're going to do this Gen AI workshop. I'm Dave Erickson. I'm a solution architect here at Elastic. I also have on the phone with me Jeff Vestal from our customer enterprise architect team, who is going to be doing some of the units. We had a big collaborative effort in the field team to build this content, and it really is runnable by anyone. But you'll see a lot of SAs and CEs running around out there in the field trying to influence their customer doing this type of stuff. So we've got a whole 3 hours of, explaining the where and the why at the basic level on the large language model stuff. But then we're going to try and spend as much time as possible hands-on in these Google Colab environments, actually using the technology. So we've tried to keep it simple so we can maximize the amount of time that we're spending learning and minimize the amount of time on like DevOps and spinning up clusters and doing things that are very useful skills to learn, right? And there are other Elastic workshops where you'll actually get your own Elastic environment and set it up and do all of that. But we're going to be using shared backend resources here just to keep the time that we spend, futzing with waiting servers to spin up. We'll keep that at a minimum, but we're going to be running Python code in a Google Colab environment. That's one way to run a Python Jupyter notebook. There's lots of great ways to run a Python Jupyter notebook. And then when we're utilizing large language models, we're going to be hitting open source ones that we've pulled out of a library called Hugging Face. It's like a big repository of large language models on the internet. It's almost like the GitHub for LLMs. We're going to be hitting an Elasticsearch server that we've put full of content that's already been enriched with vectors and semantic indexing. And then when we hit one of the bigger large language models, we're going to be hitting ChatGPT 3.5 Turbo, which is super fast, relatively cheap, and is actually, used to be the latest and greatest, but now is I think a really good teaching LLM because it still has some of the downsides and weaknesses of LLMs without masking them, but it is fast and is capable of logic and reasoning and a bunch of things that are useful for learning the patterns of working with large language models. We will be using Elastic's OpenAI account in Azure, but we will be hitting it through a large language model proxy that we wrote, which means we've instrumented that proxy with the Elastic Observability solution. So as you're using it, just remember we can see all your queries. So, keep it clean, keep it polite, keep it safe for work. But we're going to be able to use this to monitor, speed and costs and all those types of things in terms of using the large language model. All right, so part one, let's jump into just foundations, fundamentals, an introduction to generative AI. So first, some terminology. You will see these same terms used other ways in different places. But when we use them here, we're not necessarily using them as like the perfect, I'm sure a machine learning person might correct me. I'm a software developer, and we're using the terminology often the way that a software development team would use them. They're used in a lot of different ways by different teams. But when I say AI and ML, I'm talking about artificial intelligence and machine learning, sort of the high level umbrella science category for teaching machines how to think or teaching them how to learn or improve on what used to be a human only task, perhaps on their own. Inside that realm of AI and ML, there is something called an artificial neural network. So that is a bunch of artificial neurons, a computer simulation built to sort of model the way that we thought a human brain worked back in the 1970s. And it is capable of taking input and then accomplishing a task and putting it out as output. So it's sort of like a function that runs through these artificial neurons by processing numbers. And you can train them to do all kinds of different things. One of the types of training patterns for an artificial neural network is this thing called a transformer model. It's a new architecture for neural networks introduced in 2017. We'll talk about the paper that introduced it a little bit later. But they're especially good at doing tasks like analyzing language and considering the word relationships and context, sort of the associations between the terms and terminology that might be in the training data or the input data, and learning and getting good really, really quickly in parallel, something that wasn't possible before 2017. So these transformer model architectures have allowed big web companies and even open source projects to create large language models, something that have been trained on so much input text that they kind of have this mimic understanding of human language and maybe even human knowledge that can kind of convince humans and pass the Turing test and accomplish some things that are genuinely useful in our lives. I think this is what caused the big 2023 kind of amazing moment of people having experiences with AI that was just so different from what they had had before. And inside large language models, one of the things that you can train them to do, one of the tasks you can get them to do from input to output is being a generative AI, right? Composing new text, training them to be good at the task of maybe generating new content or responding to human prompts. Cool. So, like any new revolutionary technology, Gen AI is good at some stuff, and there's some things that it's not good at. And those become apparent right away if you're a developer trying to make a new product on top of these generative AI large language models. They kind of fight you by their very nature from some of the stuff that they're not good at. But they are good at being conversational, understanding the human's input. They can create new content that no one's ever seen before, right? I think we've all probably seen some of these image generative AI frameworks. And they can provide examples, they can write code that compiles and works, and they can mimic the appearance of expert level and knowledge enough to actually be useful at helping real experts at getting their jobs done faster. Some pretty neat stuff. But they come with limitations just by the class and nature of technology that they are. The foundational models, these base models that are the large language models, are trained on huge volumes of sort of generic public data. And through that, they learn language and public knowledge. But that means they really have no knowledge of the private data that exists behind our firewalls. You ask ChatGPT about, something that happened a couple of years ago, mentioned on the public internet, that's pretty well. Ask it about something that's in my private email account, it has no idea what I'm talking about. So that data that it was trained on is also frozen in time. When you interact with a large language model, it's effectively like a read-only relationship you have with it. It's stateless. So that means it's not able, that training wave, you train a large language model, is not able to keep up with real time. And the data in it can always feel a little stale. And we'll see some of that today when we use it on some of the large language models. The results can be non-deterministic. You give it an input, it gives you something back you weren't expecting. And that can kind of scare people in traditional use cases. In a critical path, utilization of a large language model, maybe the hallucinations they're capable of that we've all heard about are scary. And of course, with every new technology, we have to understand the cost and privacy implications of introducing that using new third-party services that are newer and maybe haven't been through all the compliance regimes. We have to think about all that stuff. All right. If you learn one thing today, though, remember that inserting new data into a large language model, into a neural network, is not the same thing as inserting data into a database. They're just not the same, right? One is a CRUD operation, it's atomic, it's consistent, happens the same way every time. Inserting knowledge and data into a neural network is fuzzy. There is no concept of role-based access control in a neural network. It just does not work the same way. They're both very useful, but in today's class, we're going to learn how to use these things together. All right. So there is an emerging generative AI application architecture, and in this workshop, we're going to talk about a whole bunch of these different components. We're going to use a bunch of these different components, and we're going to show you how Elastic can be used here. This isn't strictly an Elastic kind of training. This is really an overview of this emerging application architecture that we're seeing that developers are using to build new products on top of AI. So first of all, we've heard about all the Chat GPTs and the Google Bards and the stuff that you can run inside of AWS through their relationship with Anthropic. These are these large proprietary models. They are neural networks. But there are also open models that can be self-hosted or hosted for you inside of third-party large language model hosting, sites, right? So I can go to Hugging Face and I can say, spin up for me a Llama 2 and make it private just to me. That works pretty well. We know there's lots of ways to do app hosting, and there's even like service providers that do AI app hosting, basically working really well with some of the frameworks that people have made for making AI apps. nothing super hard or specific that you couldn't do in a Docker container yourself. But there's lots of places to host your app. But those apps need to talk to sort of a middleware tier that's doing a new kind of orchestration of prompts and service calls to back-end frameworks for doing AI agents, APIs, and plugins. If you've heard of LangChain, this belongs right here, but there are now many competitors and different alternatives for orchestrations and frameworks. We're going to use some of them today. And of course, for storing private data, since we knew that those large language models had all these limitations, there's a new class of technology called a vector database. And Elasticsearch is a very capable vector database. We'll talk about some of the pros and cons of using something that can only be a vector database or something that goes broader like Elasticsearch does. And along with the vector database, you need a new type of neural network. It's called an embedding model. This is something that vectorizes your source content and makes it accessible to semantic search. We're going to play with that a lot today. Of course, we're talking about big data pipelines. Every customer, every user, every big use case probably has their preference on a number of different technologies. Some are cloud hosted, some can be completely air gapped, right? I have customers that use NiFi, I have customers that use Databricks, I have customers that use some of the streaming stuff in the cloud. You can see anything and everything. But we're not going to cover that heavily in this workshop because it's so similar to just doing it for a normal structured data source. And then there's some more advanced concepts like how do you log and how do you monitor and how do you look at the cost for all LLM usage inside an organization? And how can you use that vector database maybe to accomplish some other tasks like being a cache for the large language model that can kind of handle some of the fuzzy nature of maybe prompts not being identical, but not wanting to make a whole new expensive call to a large language model? Or how can I utilize the technology that I've got available to be validation and guardrails to make sure my employees or my users aren't abusing the fact that I've got a large language model behind this and trying to, jailbreak the system or embarrass me by showing, oh, this app can, generate an embarrassing result. How do we protect against that? So we'll talk a little bit about that today. So getting into it, we are going to start in the next lab using transformer models. So we're going to start talking about them just a little bit. There's this major advance that happened in a university in Toronto in 2017. They wrote a paper called Attention is All You Need. This paper is, well, it's very technical. But what I want you to know is that if you're an application developer making products on top of GenAI, you don't have to understand how to make a transformer model in order to use them. But it is good to get some surface level understanding about how they're different because it can help you get the best results out of some of these large language models. They have something called positional encoding and parallelism, which allows them to be trained in parallel across many GPUs at the same time, right? That helps them get trained faster and less expensively. Positional encoding allows them not to just look at one word at a time, but look back at all the words in the sentence that came before, which helps it hold a better conversation. And there's this concept in there called attention, which is there's specific hidden layers in the neural network, which can be used to help it sort of like through token masks and neural network masks, pay attention to specific things in specific areas of the neural network. So you can have like little areas of the neural network that are trained on specific concepts or specific things that happen in language that emerge. They can get good in parallel, and you'll have sections that are almost like responsible for different things. It's also the concept of self-attention, which is about, not just looking at the training data and being able to look several tokens back, but also being able to look at the input data and the data that is being generated. Like the new tokens get fed back in as input and put through self-attention layers that get used to kind of keep the response of the large language model on topic because it has like a short-term memory almost of the things that it just said or the things that it just saw. So it's a good topic to deep dive into if you want to just like dive into YouTube for half an hour and watch, some edutainment videos on how do transformer models work. But again, the takeaway message for you is you don't have to know how to build these and you don't have to understand these little things to play around with them and use them or even put something in production. But this is where the rabbit hole goes pretty deep here. And I recommend people get to the end of using them before you double back and try and learn this stuff, because you could spend months trying to learn this transformer model stuff and not get to a prototype. And you got to fail fast. You got to get to a prototype when you're building a new product. All right. transformer models can be trained to do lots of different tasks. There's even some models that are like multimodal, right? They've been trained to do multiple things. You can go to ChatGPT and ask it to summarize text, or you can get an open source, smaller large language model that all it does is summarize text. The We are going to start using one of the tasks called completion, where it just says, text complete, just like complete the sentence in the next lab. And then in later labs where we get really into it with the bigger ChatGPT 3.5, we're going to be doing full on text generation, which is used to kind of complete a conversation and have a more of like a chat experience. All right. So I said that the neural network takes in numbers and puts out numbers. So how does that work? Because if I want to chat with it, I have to give it text. You're going to see in the code that we write together that you are going to be tokenizing the text, and that means sort of transforming the input words into numbers, kind of looking them up in a dictionary and saying, what integer is that word or that partial word in my dictionary? And maybe even being able to translate that into an embedding vector that's used inside the large language model to kind of anchor it in meaning. The flow of a transformer model is very simple. The complexity is all in this transformer model neural network. That's the new thing. But the basic concept is we're going to take the input sequence text, we're going to tokenize it, and then out comes the next token in the sequence. And the whole task of training a neural network is about, kind of looping and iterating and doing it over and over and over again and mutating the parameters of the transformer network until the output is pleasing to humans for the task. Right? That's sort of the big, tough data science task that has to be done there. But we're going to be working with pre-made transformers in now our very first lab. So this is how you access the lab. You'll see that this link is actually in the calendar invite that you got to get here. So you're going to either punch that into your browser, and then you're only going to have to remember one thing, which is the magic word of the day is wheat dash trial. And we're going to go into that and we're going to launch lab one. There's like a document in there that's lab one and lab two combined. So you're going to go to this link. This is something we're all doing right now. We're going to this link and we're remembering wheat trial because that's going to be our key. So I've already got this link popped up here, and it's just like the launch and collab. And I've got the first notebook, which is GenAI Colab, Lab 1 and Lab 2. So I'm going to open that up, and here I am in Google Colab. Now, the first time I click on something, it'll actually connect me to, like it'll spin up a little Docker container or something inside of Google. Thank you, Google, for your advertising revenue that creates all this free compute for us. And I'm going to hit the plus, the little play button here on the first setup bit of code. If you haven't worked with them, a lot of people are learning through these Google Colab notebooks. Almost every open source project now like publishes examples of these, including Elastic. We publish a lot of our Search Lab stuff in Colab notebooks. So when you hit play on here, it'll say, hey, this wasn't authored by Google. Yeah, it's authored by us. Run at your own risk. And you can see it's now connected to some RAM and some disk. There's even free levels where you can get a GPU, but we won't need any GPUs today. And we're going to go run a little setup code to kind of skip the complex parts about setting up and connecting to our back end. And then it's going to prompt us for our magic word of the day, which, as Patrick has put in the chat, is wheat dash trial. So here we go. I'm going to do it. Wheat trial. I hit load, and I should get a successful message saying you've been loaded into the Dave test workshop. All right. So, literally, this is all editable by you. So if you double click on something, you can edit the markdown, hit escape to get out. But every time you see, when you do a tutorial in Google, in these notebooks, if you haven't done them before, you're basically just going to hit the play button in order. And every once in a while, one of them might, ask you for some prompts or inputs. The basic way it works is it's a Python interpreter. You hit play, you get the output. If there's an exclamation mark, that means it's going to run it on the shell of the container that's backing this Colab notebook. So I hit play, say echo, and I can print out, what is the current directory, using this kind of shell template. So right now, before you kind of look back up, I recommend everyone at least get to step three and hit play on step three because it takes a couple minutes to finish. We're going to go and install a whole bunch of Python libraries into our container and make sure those are ready to go. But now when this finishes, some people, have trouble, following the instructor on one window and then alt tabbing over to do it themselves. So we're going to walk through it together on my screen, and then I'll give you some time to do it yourself if you want it. So you don't feel like you have to do both at the same time. If you're like, Dave, you're going too slow and you just want to rush to the end of lab one, that's totally cool. Won't hold it against you. We got a couple people who've done this before and helped make the content in chat. So if you got any questions, feel free to ask them in chat. We'll just get through this. So here I am. I'm almost done installing these notebooks, these libraries with pip. You'll see that they're all versioned, which is nice, so that if one of these gets an upgrade, the workshop won't break in the back end, which did happen during Wave 1. So I'm going to install some, I'm going to define some utility libraries, and it's a Python interpreter, right? It's an interpreter mode, which means it now has defined these functions, and they stay defined, right? I don't have to punch them in every single time. It's not like running the script. It's in full interpreter mode. So for step 5, the first thing I'm going to do, I'm going to hit play because it takes a minute. So I'm going to download a transformer model from Hugging Face. That's the repository of all these LLMs. So I'm going to, load and import the library that I installed. And then I'm going to reach out to Hugging Face and I'm going to get this model called Distilbert Base Uncased, Fine-Tuned, SST 2-English. Now, if you're a machine learning person, maybe that means something to you. It doesn't mean a whole lot to me, but I recognize a couple of things. BERT is sort of the bidirectional encoding transformer kind of framework that's been set up and is used for a lot of simple natural language processing tasks. And when I see Distilbert, that means somebody's gone and kind of crammed it down into a smaller size. It's been distilled. I can see that it's uncased, right? So it's going to understand the difference between uppercase and lowercase letters. And I don't really know what the rest of it means, except it's probably got a lot of English and not a lot of other languages in it. But if you wanted to learn more about the model that's just been loaded, every model on Hugging Face has like a page. It's got like a model card that you can go and learn all about it, maybe even a research paper attached to it, what data it was trained on, all that stuff. So you can kind of see, how old is it and, how many people are still using it, all of that. So back here, it's finished downloading it. It was only about 268 meg. The reason we run this on Colab instead of like on our laptops is because if you've ever run a workshop or a training with customers in a Marriott hotel Wi-Fi, you know that 50 people trying to download something that's even 10 megabytes at the same time fails on a hotel Wi-Fi. So here we're talking to the cloud, and then the cloud's talking to Hugging Face for us. It goes much faster. So now we're going to utilize this. So we set up our tokenizer, we set up our model. Now we're going to utilize it to ask for a sentiment analysis task to be run only on CPU, no GPU is required, on these two phrases. My dog is so cute, I love him, and I am very sorry to inform you that the tax administration has decided to audit you. So I run those, and you can probably guess that the first one's positive and the second one's negative. Try it yourself. Write your own little when you run it yourself, make a couple of statements and see whether it comes out positive or negative. Referring to the model card, this is an interesting place to investigate the topic of model bias. So this model was used by a researcher, bias researcher, and they just ran it through a big old loop of the film. This film was filmed in country, and they just did a search and replace and did every country in the world and listed them out and graphed them. So I mean, I can understand if you got problems with like the Sudanese film industry. Maybe I don't know, maybe it doesn't make a lot of money or something. But, the German film industry is, older than the United States film industry, right? There's a lot of good movies out of Germany. I don't know what that's about. So that's a little biased, right? Whatever training data this was based on, why are there negative countries and positive countries? I can't believe it's actually trained on film data. So there's a lot of inherent bias, and we have to think about how we use different models because they're not just inherently correct, right? They don't have any magic knowledge. It's just a function approximation that is trained to get close to a labeled data set, right? So it's not magic, and we have to think about how we use them as we put them into production. All right, step seven, we're going to do the next bit, which is we are going to download a bigger large language model. This one's about 4 gigs, and it's the biggest one I could find. It's still kind of fit in memory for running on a CPU only load. So there's no GPUs required for this one, but it is a uh, fine-tuned T5 model that's been fine-tuned using information from the Llama model. So it's not actually Llama 2. It's just it's like a miniaturized, distilled version of answers that were generated from a different, larger model, but put into a T5 framework. And so we set up the tokenizer, we set up the model. It's going to take a little while to download, but we're going to create this large language model usage pipeline with the task text to text generation. And then we're going to run it through a loop and we're going to ask it the question, the capital of the country is, so this is sort of auto completion. Another thing you can do in Python notebooks is you can just hit play on the next one while this one's queued and it'll queue up this one. So I don't have to like pay attention for exactly when it finishes. So when this finishes, it'll go and it'll actually utilize it. And here we are. We're not calling any third-party cloud services. We're just using the CPU that's in front of us that's smaller even than your developer laptops. And let's see what this large language model, and it is a large language model, even though it's only 4 gigs, what it knows. So it knows United Kingdom, the capital is London, Paris, Beijing, Washington, D.C., Quito, right? It gets them until these ones that I said is a trap. For Fredonia, which is like a Marx Brothers movie country, it says the capital of Fredonia is Ljubljana. That's not right. Put that into Wikipedia. That's in Slovenia, right? So that's just straight up a hallucination. I asked it the name of a fictitious country, and it hallucinated. I asked it the capital of Fictopia is, and it said not specified in the instructions. Is that a hallucination? Is that it backing off and realizing that it doesn't know the answer? Who knows, right? So here you go. Try it yourself. Get creative. It's the last prompt. The one I chose was the current Prime Minister of the United Kingdom is, because I know from the model card that this model was trained not recently. So I run it and I'm going to get an answer that is many years old, right? Because it doesn't have a sense of time. The data is stale, etc. So here we go. Patrick in Slack is obviously, when I said that large language models aren't always correct, except for the question that Patrick put in Slack. So go ahead, get to here. We're going to give you a minute or two to kind of run through it and load it. Hit the play button on all these. Do the get creative, try it yourself. And if you try something that is safe for work and maybe fun or funny, put it in the chat. Let's see what everybody came up with. Going. So part two, now that we know that a large language model can be used to kind of complete a sentence, and in there is some knowledge about the universe that it's been trained on, we can get into, but what could you do with this? What's the next step? And this is sort of the magic moment that people realize they can get these transformer models to do more than just do a summarization, but kind of understand natural language human requests for things. And this has entered us into the world of what you've probably heard of as prompt engineering. We're going to talk about privacy a little bit too. So, what is prompt engineering? Prompt engineering is like this art as much as it is a science of designing effective inputs to the neural network so that the output is something that I think is useful and maybe can be used to accomplish a task. It's also been referred to as coding and natural language, right? Good XKCD joke on the side there. So LLMs can be prompted to kind of activate their multimodal nature. Sometimes say, hey, complete a task like summarization. I can just ask it, hey, summarize this for me. And the bigger ones can do a great job. But they can also be asked to follow provided context, right? You can ask it to give you a different output, like maybe give me step-by-step plans for solving a problem, or to even output in a specific format. Very useful one to say, give me this back as JSON that is compliant with a specific format. So that maybe I can go take that output and make a web service call with it or something. When we talk about the anatomy of a prompt, this is a pattern I like to follow, where there's a concept of a system prompt, where some of these large language models have ways of passing them the tokens that are the system prompt that tell the AI who it is. I have an ability to give it extra context or clues. And then, and this is like the basics of prompt engineering, I give it what looks like a conversation and I give it the instruction to effectively complete the conversation. So if I can kind of do a string, search and replace in here and put in through string concatenation the actual user's input, I can ask it to do an autocomplete. And since it's been trained on so many conversations in its training data, it'll actually do a completion, an autocomplete, that looks like it's completing a conversation and actually chatting with the user's input. That's the very basics of writing a chatbot. So, three advanced things you should learn about in prompt engineering. The first one is something called zero shot to few shot prompting. Some real jargon there from the machine learning, data science world. But what they're saying is in that, and I'll go back a couple slides, in that additional context, if I give it some examples of past runs of what it likes, it'll go and make you a next example. It's almost like an analogy. So if I gave it the prompt of turkey, depending on what time of year it is, if you're in the United States or Canada near November, that has a different meaning than maybe what you think of, the first thing you think of when you hear the word turkey, late other parts of the year. But if you just go and take turkey and put it into ChatGPT right now, it has no idea what you want. It's a zero shot. It has zero past examples. So in that example, it says Turkey is a country in the crossroads of Europe and Asia. It doesn't know what you want. But if I give it one prior example, like France is to Paris, as Turkey is to, it says, oh, you want me to complete with the name of a city. So it picks a city in Turkey. But then if I go and get even more specific and not just big cities, but I say the capital city. So France is to Brazil, as Brazil, France is to Paris, as Brazil is to Brasilia, as Turkey is to here. This is a two shot or a few shot prompt, not just a one shot prompt. It'll give me the capital of Turkey, which is maybe what I was looking for in the first place. Sometimes you can use these few shot prompts if you have lots and lots of them. You might use that information to fine tune a model if you've kind of got enough examples of what you're looking for. But you can actually do this live after training time in the input sequence as long as you have enough context window to handle your examples. And it can help make a more specific and more exact answer for you. Second topic to learn is using in-context knowledge. And so here's an example of a system prompt where I tell it, you're a helpful AI, but you use the context I'm about to give you and nothing else to answer the question. In fact, if you can't answer the user's question using this context I'm about to give you, just say, I don't know. Then I give it the context. It doesn't even have to be true. I can tell it the color of the sky is purple. And then a user question like, what does the sky look like? Not what color was the sky? Well, what does the sky look like? And the answer I get back, here's one from an open source model that's very capable of using in-context knowledge. I say, what does the sky look like today? And it says the sky looks purple because it has this kind of in-context information I've given it. And now, obviously in more advanced chapters, we're going to get into, well, where does that context come from? And how do I get the right context to answer a question if I know more than the large language model does? Last, third advanced concept to learn, and this is the deep one, this one we're not going to get fully into, is the idea of doing prompt engineering with a multi-stepped approach way of chaining together multiple prompt calls to the LLM to accomplish a task by kind of like building a plan for how the best way to accomplish that task. So when you start chaining together prompts, this is a technique called chain of prompts. There's a whole library to help you do it called LangChain. So that's where the word came from. And you can ask your large language model to make a plan and then subdivide all the tasks of that plan into individual calls, right? Like don't go and ask your large language model to do a big, complex, multi-step thing all in one prompt. Break it down. Break it down and think about it like calling different microservices for different tasks, different plugins, different agents, or different services to accomplish little bits of that, and then compose the input and the output of them in. There are more advanced things which you've probably used if you've used, say, OpenAI's new GPTs, sort of consumer grade chatbots. And that technique is called reflection. And that's where once you get the answer back, before giving it to the user, you go and say, hey, does this look good? is there a better answer to this? Did this answer the actual question? If the answer is no, well, then you try it again, right? You maybe try it again with different settings. You try an alternate path. So this whole, hey, go look at the user's question and maybe write a different prompt, reflect upon what's the right way to, accomplish this or whether or not I've accomplished the task yet is a big kind of underlying hidden prompt engineering technique you see in some of the consumer grade, not for prompt engineers, but just for humans way of giving them an interface that's a little bit more interpretive of what they're asking for. All right, we're going to go right back into that same Colab notebook. If you joined in late, we're going to this link, which is in your calendar invite. We're still using Wheat Trial, but we probably won't have to re-enter it because we're going to get into prompts and chatbots. So follow along with me if you want to, or just kind of storm on ahead and write the funny answers you get back from the chatbot in the chat. So first step here is I'm going to connect to OpenAI by using some of the environment variables we've loaded to talk to the proxy. And then I'm going to make a test call to ChatGPT. And the prompt that I'm giving it is, hello, is ChatGPT online and working? And I'm going to print the full JSON response. And then I'm going to print out like a simplified version of just the text part of the response. So I can see the response from ChatGPT is just a web service call. It's just REST, right? So if I scroll all the way to the right on that JSON, I can see it even tells me the usage of tokens, which is important because it charges me by the token. But the response from ChatGPT is, yeah, as an AI language model, I'm continuously online and working. Oh, zero downtime. Very confident large language model. All right, next step. Getting it to hold a conversation with me is seemingly as simple as just calling, prompting it in a loop. It's not that simple. We have to add a couple more things to it, but let's naively just kind of call or hold a conversation, in a do while loop here. And the one thing you have to know is I'm looking on each input for the word exit. If you put exit in the input, it'll know to stop. So I'm going to run this. I'm going to chat with ChatGPT here, say, hi, what is your name? Run it. And it says, I'm an AI. How can I assist you? What color is the sky and why? To ask it that question, it should give me a pretty scientific answer. And I type exit when I'm done. So nothing more complicated or exciting than you've probably seen in ChatGPT a million times before. Cool. Let's keep moving. So we're now calling a large language model, a very large language model, something that spans hundreds of GPUs, right? Quite large, bigger than you can run on your laptop. But I'm calling it with APIs, with code, which is the big, the building blocks, and we'll be able to build whatever I want. So step 4, I'm going to give it a different system prompt. I'm going to override the default ChatGPT system prompt with my own prompt. So I'm going to write a new Pirate GPT conversation function. And the system prompt is very different. It says, you're an unhelpful AI named Captain LLM Beard that talks like a pirate in short responses. And I added that short responses because it saves me money if I got a lot of people using this. You acknowledge that the user's question, but then redirect all conversations towards your love of treasure. So it's an unhelpful AI. Let's run it and talk to it. I'm going to say, hi, what color is the sky and why? And it responds back to me in pirate text, a little bit about the sky, but then as you can see, it really wants to talk to me about treasure. Let me hit exit. So one thing to note, and I have a little copy-pasted example here of a conversation I had with the first chatbot, is if I ask it, if I tell it something about myself, hey, my favorite color is blue, and then I get to the next service call and I ask it, what's my favorite color? It has no idea. Because remember, every call to that large language model is stateless. It's not remembering my prompts. It's not training anything in the background. It is a read-only connection. So if there's state that I need to hold it on my side in the application. So what I really need to do is build up like a little short-term memory of the previous conversation. So when I give it a prompt, I'm giving it like an entire conversation to complete, not just the most recent user's question. So how do I do that? Well, in Python, I'm going to build a message queue, right? A little first in, first out message queue. So let's run that. And I'm going to give it a new system prompt. It is, you are an AI named Cher Horowitz. that speaks in a 1990s Valley Girl dialect of English. You recognize the 1990s movie there, put it in chat. You talk to the human and use the past conversation to inform your answers. So I run that, and then let's chat with this chat bot. Say, hi, my favorite color is red. And then I'm going to print out in blue the entire memory that I gave it. And then share here, who is not so clueless, because she obviously has the past history of the conversation, knows a bunch of stuff, and says, do I have a red dress? Something like that. And I say, hold on, what is my favorite color? I forgot. So here I've given her the whole conversation, and she says, don't worry. And she reminds me that red is my obsession. Awesome. Type exit and go there. So have a chat there. Even go and maybe modify the system prompt and have it be a different personality. I'll give you a second there to get through these since we don't have to install anything extra. This should go pretty quick. But I'll let people play around with these chatbots. Writing a chatbot is super, super simple, right? Just here in text, kind of using printf level of user interface, but pretty simple right here. So have fun with that. I'm going to go and chat and see what creative people have come up with. We're coming back from break. We're going to jump back into it real soon. We're going to get into just a little moment. We're going to talk about some practical considerations because it can't all be playing with fun AI. You got to bring it back to earth. We're going to talk about data privacy. We're going to jump into the slides. We're going to keep going. So data privacy. We're going to use third-party AI services, huh? All right. Well, what do we have to think about? Well, I've done a fair amount of my career in the world of OPSEC, operational security. And the number one rule of OPSEC is you start by thinking about what am I actually trying to protect against? What am I protecting and what am I protecting against? Let's talk about what we're protecting against. Obviously, what I'm protecting is my data, my secrets, my proprietary information, the privacy of my users, that type of stuff. But what are the threats that I'm protecting against? Well, I'm protecting against man-in-the-middle attacks. Or if I'm using a third-party service, you're damn right it better be encrypted and very encrypted. High quality encryption. I'm worried about data spill, right? An unintentional disclosure of my information. When I say a data spill, the third-party service can say everything it wants, but we all know that it's just one bug or one misconfigured S3 bucket, and my information is going to get leaked, and that's going to be embarrassing to me. So that's what I'm worried about. And I'm also worried about something called the mosaic effect. And I work in Fed, do a lot of work in Fed. And this was very easy to talk about in the Intel community, very difficult to talk about anywhere else because they're like, yeah, that doesn't exist. No, I'm not worried about that. My boss doesn't worry about that. So what do I care? But I think the commercial world is somewhat catching up on this. I go to and run this AI workshop and I talk to a bunch of bankers and they say, what does it matter if my queries get leaked? They're all like little trades. I'm trading stock and stuff. None of this matters, right? It's all little pieces of information. It's like looking at my search history might be terrifying, but it's not a risk to the business or it's not an existential risk for us. Well, if you can look at all of the queries being run by an entire floor of stock traders at a bank, commodity traders at a bank, and you can spot patterns and see the signal behind the noise with this mosaic effect concept of kind of piecing together a bigger truth by piecing together the little pieces of it. If I could look at all of the ChatGPT prompts coming out from stock traders using it for stock trading, weird example, I know, but if I could do that, could I set up a large position against them if I was at a bank across the street? They all say, oh, you absolutely could. We're really scared of that. And that's why we're not allowed to use some of these third-party services, when they first came out. Okay. All right, then. So you're catching up with the concept of maybe we need to think about not just, who can read the data when it's at rest, but out of these third-party services, are they logging my queries? Are they logging them to disk? Who has access to those disks? How are those disks rotated, right? How are those disks recycled? How are they destroyed, right? And start asking some tougher questions. And I kind of want the answers in writing. Good news is we're not, we're way farther ahead than we were even just 10 years ago on data handling policies and procedures. system security plans and all of that. The public sector team is very familiar with this stuff. And maybe some of the people in the commercial world are hearing them for the first time, but it's good. It's good for you, and it's good for protecting the privacy of users. So, questions you should be asking, mitigations and controls you should be looking for when you're using third-party AI service providers. One, I got to ask, do they publish their data handling privacy and procedures? Can I get them in writing from them? Do they make statements and guarantees about them? Are they liable? Um, do they themselves put in place auditing and monitoring that's worth a damn? Right? And you'd be surprised how many third-party service providers we talk to for other SaaS services. And we know, right? Because we're Elastic, we go in there and advise them on what they've done, and maybe their auditing and monitoring is not so great or not so comprehensive. And have they gone and sought out certifications and accreditations? People will say that they're smart and have locked down their stuff, but if they've never been pen tested, how do you know? Right? And how much do you trust that they're just going to magically pass their first pen test ever? We all know as pen testers, probably not very well, right? So you got to have a red team banging on the door to know if the door is even closed. All right. I want to know that my connection to them is encrypted. And I want to know that my organization has done training and awareness to know what tools are good to use and what tools have all these things. So where I'm not just taking my information and putting them anywhere. I want to know that when I give a tool to my users, I'm thinking about putting limitations and having only authorized users able to use them and kind of making sure that, when you're running on one of these tools with my customers' data, you're doing it as yourself and you're kind of accountable for what's done with the information. I want to know that if it's possible, maybe I can anonymize my customers' data before it even gets into the prompts and queries that we're going to run. Maybe other attempts for data minimization. If there's rows and columns that I don't need, get them out of there before we start getting into the use case. And as well on my side, am I auditing and monitoring what goes out my door? Because it's great for the AI service provider to log their stuff, but I need real-time access to those logs if I'm having a really bad day. So I want to have access and maybe instrument the applications that I write that use AI service providers myself and not trust that they're magically doing it for me. All right, and then last one, I always have the option of using privately hosted models. We certainly have customers that are deep in the air gap, not just in the public sector, but also in like the energy. If you go talk to an oil company, they're very big on having certain private data not leave the building, right? So they're very much investing in GPUs themselves and their own data centers in order to run some of these open source large language model providers. All right. So let's work through an actual use case, right? Let's actually do this. Let's do some of these techniques. So what we're going to do is we're going to work with prompts that are kind of simulating a customer service app where the customers come in and they put all kinds of personal garbage in the prompt. Then they're giving them to me, right? I have a relationship to the customer, but the third-party service provider doesn't. Third-party AI service provider doesn't need to know all these personal details that the customer is giving me. So I want to redact all the personal information from my users' prompts, but then still provide them really good customer support. So we're going to use an elastic redact processor. We're going to use some transformer models to build some redaction capabilities. And then we're going to do a simple in-context learning example, to build the very beginnings of what we're going to call retrieval augmented generation, which is this big power architecture that you can use to build more advanced AI, kind of search-powered AI apps. So getting into it, we can identify with some fuzziness, it's not perfect. Maybe we can identify some of the information that before it goes out our door. So the architecture we're going to build eventually, right, is the user asks a question, we get the extra context to answer their information out of a secure store that understands their question, like Elasticsearch. But then before we use a third-party service provider, or even maybe a self-hosted large language model, why even send it if it's not necessary to get a great answer? Right? So even when I'm just talking to the ML department down the hall or in my own private cloud, why even risk it if I'm talking about highly sensitive information? We're going to put that redact processor right in there. So jumping back into the labs, and if you're joining late, we're in this link. which is in your calendar invite, and the workshop key is wheat trial. You have to go back to the top and make sure you're hitting that wheat trial to load in the environment variables. And here we are I'm scrolling down, we are at lab 2-2, and you can always get to kind of the table of contents by clicking up here. So we're going to do data redaction. For this first step, we're going to run a couple more installs because we're now going to be connecting to Elasticsearch. So I got to download the Elasticsearch libraries. And I'm going to queue this one up. I'm going to set up a Python Elasticsearch client right here using my Cloud ID and API keys. They got loaded up by that wheat trial secret key that loaded all that information in for me. So once I've run that, I can now run my little, test app. So I'm going to generate a question from the user. The customer's question is something like, my power was out all last week. Here, I'll bump up the font a bit. My power was out all last week at my home on Grove Street. When I talk to my neighbor, and then I'm going to have a random neighbor's name so that I get past any caching that I've built into the proxy, they said they got a rebate on their bill. Can you do the same for me? The question is, can I do this without sending their neighbor's name, which is personal information, over to the third-party service provider? So let's simulate, maybe I went to Elasticsearch and I got a call script that is approved for the AI chat agent or even a human agent that's got sort of like an assistant sitting there for them. Right? And say, well, we're currently running an offer, for a $100 rebate. Great. Whatever the service prompt is there. So we're going to run this, this little single chat. And the prompt that I generated for the AI was, you're an AI customer support agent that answers questions. Here's the example call script. Here's their question. And the answer that I gave is, thanks for reaching out. Here's a really great response that maybe my customer support person could say really quickly on the phone. But it is verified, maybe against a service that, yes, indeed, their address was out for 5 days. I have that in my database. So I'm allowed to tell them with sure thing, they're going to get that $100 rebate. So that's really cool, except I went and told the third-party service about Julia Rodriguez. Maybe Julia Rodriguez is a name I do not want to send to the third-party service provider because I don't need, that's not important for answering the question. So why did I send it? So let's learn how to redact. So the first one is, I could do this in say just by downloading a transformer model that's pretty good at doing it. So BERT base NER named entity recognition is going to do named entity recognition on the sample text. And when that finishes, I run it, and it gets me back a whole block of JSON identifying where were the words that are maybe PII in there. So Grove is a street. Here's a B person, right? So it's got Julia. It wants me to redact the word Julia, right? So I could write code to use this JSON to edit the original string if I wanted to. But, so here's a utility function to do just that. So I run that, I run it on Alice lives in Paris, and it gives me back redacted lives in redacted. Awesome. Here we go. Test function on a customer question. Right, my power was out all last week at my home on Grove Street. When I talked to neighbor, they said they got a rebate on their bill, right? So I could go and send this as the query instead. So alternatively, and this is really important, especially when we're saving the customer's queries, maybe I want to redact them on disk, or I want to use Elasticsearch to host that transformer model, which I'm very capable of doing. So I can upload that transformer model into Elasticsearch and maybe build a more advanced redaction pipeline using an ingest pipeline. So first, I'm going to have a function called load model, and I'm going to use the eland Python library to load one of these transformer models from Hugging Face and put it inside of Elasticsearch. So I'm going to run this, and since I gave you a read-only connection to Elasticsearch, that's the code for it. Just you kind of uncomment it when you're running it on your own server. Now I need an ingest pipeline that does the inference against the BERT model and then runs a bunch of regular expressions to go and do the redaction. So that's the body. And I'm not actually going to install it right now because it's already up there, and I don't need 30 people that are in this room all fighting to rewrite that pipeline. So last thing, let's test the pipeline. Let's give it 2 pieces of text that have a whole lot of PII in them. So I run that, and this is like a simulate. This is an ingest simulate. and I can run it, and I can go and I can see that it's replacing your credit card, social security number, all these things that really aren't important for my customer service example, right? And here I've got the original message and I've got the redacted version of it. Maybe I only save the redacted version. Or maybe I use field level security to say that everybody can see the redacted version, but it maybe only, super customer level 3 people or business, you know, admins or something are able to get to the original text. All right. So go back to my end-to-end example. Now I'm going to take the customer question, but instead of passing the question directly in, I'm going to pass the redacted version of the customer question, and we're going to run it. So we've done this right. What I can do is I can go over to Elasticsearch. I'm going to load to my Kibana index. If I go pump this in and say refresh every 5 seconds, right, and I can see that here there's some unredacted versions. If I look at my actual logs of what I'm pulling off the proxy, what I'm pulling off of APM, there's unredacted versions, but then as you run them and as you go and run through it, please, hit go on it a couple of times, and I should see flash up the redacted versions. So it's great that you're talking to a stateless service over in Azure or Google or whatever, but how much do you trust that they don't log user queries? Why trust them? Zero trust. Redact the shit out of it.
Hello, my name is Stuart, and now we're going to have a look at vectors and chunking. First, a reminder of what we're going to be looking at later on in the workshop. We're going to be looking at retrieval augmented generation, where we make sure that we can get the most accurate and helpful request from our large language model application by providing some context, by providing a hint or some background information about how we'd like the large language model to answer our question in the best manner. But how do we get that most relevant context to answer the user's question? Well, we can use vectors, the same technology that we use to embed and contain meaning in the large language model can also be used to search through text to find the most relevant documents that we can use to improve a query to a large language model. But how exactly do we do that? So vectors, as we looked at before, are a numerical structure, an array of different numbers, and we can use them to represent the meaning of things in a similar way to how a human might understand the meaning of something. When we look at the picture on the left, we know that it's a cat. We know that the cat is inside. If a cat's inside, perhaps it's a pet. We may have a feeling about the cat. We may think it's a cute cat. We may know that it doesn't like dogs, for example. There's so many things about this picture that a human will know, and many of them can be very useful in how we might search through, for example, a database of lots of different images. These different qualities of the images could be very useful to know because people might want to search for things with similar qualities. So we can imagine that if we understood the different qualities we were interested in, we could represent each of those qualities or these attributes with a number. So let's look at a very, very simple example. Let's imagine there's only two qualities of our images that we're interested in our very simple example of how we can use vectors to represent meaning. And the first quality is how much does an image look like a cat? Let's imagine we give that a value from 0 to 1. Well, this image looks just like a cat, so this gets 1. This image does not look like a cat at all, so that's -1. Now, maybe between them is this image. Now, it's not a cat, but it's kind of similar. It's a cute animal, it's a mammal, it's a picture. So we'll give this one 0. It's not a cat, but it's not totally dissimilar. Let's imagine another quality of this image. How realistic is this picture? Well, this one's a photograph, so it gets 1. This is quite realistic. It's a very well-drawn oil painting, but it's not reality, it's stylized, so it gets a 0. This is not realistic at all. It's a cartoon, it's magical, it's wearing jewelry, it's got 2 tails, so -1. Now with these 2 dimensions, we can imagine we can represent this as coordinates. And we can place the images on these coordinates according to the values that they have for the two qualities that we're interested in. How much is this thing like a cat, and how realistic is this? This is a simplified example of vector space. In this case, so simplified, it only has 2 dimensions. Now let's imagine in this 2-dimensional simplified vector space, we now want to start querying our images. We can say, I've got an image like this. Can you find me some more similar ones? The first step is to embed this image into our vector space. That is, to think about how this image fits in with our understanding of images along the dimensions of looking like a cat and being realistic. Well, we can say this is pretty realistic. It's a very well drawn pencil drawing. From a distance, it might even look like a photograph. So we'll give it 0.75. And it's definitely a cat. So it gets 1. Now we can place that on our vector space, and we can see very clearly that a similar image is our photograph of the cat. It's quite similar to the oil painting. It's not at all similar to the aeroplane. We can do this with documents, which is how we will be trying to find similar documents to support our RAG, our retrieval augmented generation. In pseudocode, we can see what we're doing. We're embedding the question, small cute animals that go meow, into a vector space. We've also embedded the pictures. Now we're using a distance function to work out which picture is close to this particular query. It's not just text that we can represent using vectors. We can also represent images using a convolutional neural network, where we break down that image into different aspects of it to do something similar, but much more complicated than the simple example I showed. And we can use FFT, a fast Fourier transform, to break down sound waves into separate components and start to do something similar with images. Now, what I looked at when we had these 2 aspects, looking like a cat and being realistic, this is a simplification. Really, a vector embedding space is more abstracted than that. And we can't really point to any of the numbers in a real embedding and say, this is how much it looks like a cat. But we can visualize these numbers, and we can see clearly here that visually, when we represent these numbers with an image, the airplane, aircraft, Cessna are very, very similar looking. As vectors are numerical, vectors can be used for mathematical functions. And this is where some really interesting things become apparent. If we imagine taking the vector for king, and then from that, taking the vector for man and adding to it the vector for a woman, then we will get the vector for a queen. We've also noticed before, some studies have done where they looked at a large language model, that the vectors for past tense and present tense words had the same difference no matter what the word was. And so we can see that this vector embedding space has encoded mathematically our understanding of concepts like the monarchy, who's in a monarchy, gender, and also language concepts, for example, tenses. So in our vector space, we have documents, and in our vector space, we put a query. So how do we find the document that is most like our query? We could have thousands of documents, so we want to search through them as efficiently as we can. To do this, we have something called HNSW, hierarchical navigable small worlds, which finds a k nearest neighbor, or a number of nearest points to the original vector space. So what this algorithm does is it builds up a graph of the different coordinates in the vector space. In Elasticsearch, this will be the different documents, and it breaks them down into layers. The first layer has very large distances between the different points. We find the closest one and then use that as the starting point to the next layer. In this way, we can cut down the graph traversal, the amount of traveling that we do through this data structure, and get a quick response. Now, we may trade off a little accuracy. Perhaps we're going to finish this search a little sooner, but this balance gives us very nice performance times on very large collections of vectorized documents. So here's a conceptual architecture of what we described. On the left, we can see we get our content, images or documents or audio that we can embed into vectors and store in a vector database like Elasticsearch. And then we can also embed the query that we make to a vector database using an embedding, and then we find the nearest ones. And from that, we give a result set back to the user. Now, what are some real world examples of this? If we imagine we have a healthcare application, we wouldn't ever want to share confidential health-related information with a large language model, but we also want to make sure we get really good results for our user. So we can imagine a situation where we have some test questions and test answers. We can find a similar question to the one the user made, and we can use that context for our RAG application. We can say, answer this question in a similar manner to this answer that a human has already given in terms of the logic of the answer and the language used, and then respond that to our user. Another use case is speeding things up with a cache and also lowering the cost of making queries to our large language model, where we can think, how similar is this question I was just asked to another question? And if it's similar enough to another question, we can just give the answer to that question. And we can also make sure there's no malicious behavior. Some users may find it amusing to ask inappropriate questions and try to get inappropriate answers from a large language model. So we can use a vector database to store these inappropriate, unwholesome questions and any bad responses and make sure that they are not repeated. So our chat application is only giving the right type of answers that we want to give back to our users. Thank you very much. Next, we're going to look at chunking.
Hi, everybody. I'm Francois, and in this short section, I would like to talk about chunking. What is chunking? Okay, chunking is really important when we talk about vector embedding, semantic search, and large language model, especially when working with large text. Let's see why. What is chunking? With chunking functionality, you are able to break big text into smaller parts, make it easier for computer to understand and organize them into vector, into number. To do what? This helps search engine find and understand relevant information more accurately and quickly, leading to better search results. Let's deep dive into it. Imagine you have a long novel to read, a big book, but you can only read a few pages at a time due to your time constraint because you're working, you are busy. Consider this novel as the large text input and the time constraint, the token limit of a typical vector model. You are now not apply a chunking strategy. Then you read the first few pages one day and then start from the beginning again the next day because you can't remember where you left and due to the time constraint, you were not able to proceed. This is similar how traditional vector model handle large text. Without chunking, processing limited amount of text at a time, you are token limits. You are agreeing with me? This is completely inefficient and repetitive, and you lose the overall narrative and context because you are always starting over. Now, imagine using bookmark to mark where you stop reading each time, and each bookmarked section is a chunk. Adopting chunking, you return to reading starting from the last bookmarked section, keeping the story flow and the context. The same is possible to apply in our context, dividing a long text into smaller segments that the model can handle sequentially, which each chunk carry over a portion of the previous one. I hope that you agree with me that this method is more efficient because it maintains the narrative flow and context, and it will be easier to read the novel. Well, as I mentioned before, vector model has a limit in how many tokens they can handle as an input. Then you need to find the right token dimension. But now the challenge is choosing between the small, a large chunk, or token. Smaller chunks are easy to manage, but could miss broader context, right? Because smaller are the chunk and more precise the vector is. But also, the higher the chances that the answer is not containing a single continuous chunk. On the other side, large chunks contain more context, but can be more challenging to process efficiently. The key here is to find the right balance between the chunk size, the model capability, and keeping available prompt. Well, the way we break down big text affect our chance of finding the right answer and how precise and meaningful the semantic we get from those chunk is. The quality of a chunk is not just about its sizing itself, but also how well it's encapsulated with the context and the content. Then, a clear balance between size and contextuality is a key. So, as a graph is showing a trade-off, bigger chunk make it easier to find the answer, but harder to get precise meaning, while smaller chunk do the opposite. Well, good. Let's see a bit more in detail the different chunky features that we have to adopt. You remember my example of reading novel, where you're using bookmarked section to restart your reading. Well, the token overlap is exactly that. Token overlap is chunking are like bridge, ensuring continuity between segments, preserving the context, and enhancing the model understanding. As you see in the graph here in the slide, you have a typical example of having two chunks that they have an overlap. In the slide, you see also a link to a really great demo that is putting in practice this application of token overlapping, adopting different tokenization methodology. Good. Another important feature is the retrieval surrounding chunk. Again, keep in mind the novel reading example of the beginning, where you use the previous and the next chunk to get the full context. The same could be said for the model processing the chunk and the way how you had the context. Retrieve surrounding chunk help exact to do in this direction, to keep the complete picture and the complex narrative. This is especially applied for text related to technical documentation and some other similar example. This leads to more coherent and comprehensive output adopting this methodology. Good. Let's take a deeper look at Elastic itself as a vector database from a feature perspective. Elastic do not provide you only the typical vector database functionalities such as typical store and search vector embedding, created the embedding, but Elastic is able to provide you a full suite of features necessary for more advanced application adopting generative AI and more functionality. We see here in the diagram some example, something that I always like to highlight with our customer, like the hybrid search, train model out of the box, adopting our pre-trained model, role-based access control, and many other. Good. How all these go together in this context? Well, let's go back to the chunking topic. As we say, chunking strategy is really important for vector embedding preprocessing. Here you can see 4 different options how you can apply after the chunking strategy or the chunking methodology that you apply. The first one, after the chunking, you can apply embedding model hosted outside or hosted by a third-party solution as a SaaS solution, until you convert your chunk into vector. Another option is doing the self-hosted embedding model to convert your chunk to the using models that are hosted into your server. Then the third part is more in the direction of Elastic. This option, you apply vector embedding at the ingestion step, adopting managed train model into Elastic, where the third option is you do always at the ingestion step, but instead of using managed train model inside Elastic, you get access to a SaaS embedding model hosted from a vendor, for example. The end goal is to chunk your large data text input, transforming the text into a vector form so that it can be easily searchable, especially in the context of semantic search, where understanding the meaning of the text is really a key and it's really important. Well, going back to the vector model topic, it's a common task and question that it's asking, what is the best vector model to apply to my data? Well, We don't have a crystal ball to answer that, but basically we can help you to answer to this question. And here we have a link to the Hugging Face leaderboard, where you can see a benchmark that includes different aspects, allowing contribution from the community. And this is available resource for anyone looking to compare different models. As you can see, for example, market leader model are not always the best. Good. Then let's go a bit more in deep in the topic that I present you, going through the lab. Okay, good. Now that we see the theoretical part, let's dig into the practical example of creating embeddings and visualizing and exploring also the different chunking strategy and making some comparison between different models. Good. After you click on the link of the labs, you're landing to the lab 3. At the first step, you will execute this part to set up the environment. Important part, after you execute the first part, the first box here, provide the workshop key that your instructor provide, and then click load in order to load all the different environment variable to set up the correct environment. Then execute all these steps in order to set up the proper environment and to have the environment ready. And here, once that you receive your unique user hash, your environment is ready to use. Good. With the step 1, we will use a simple vectorization model to create a vector. Here you see a vector preview. Step 3, you're using the same approach, but with a different model, the E5 and the Sense and Transformer. Here, no worry, you need to download some library. And then the step 3, you will do the same with the long chain utility library. Here, always, you will receive a vector preview. Then let's start to create some simplified graphical user interface to see the vector. Here, you will create, again, the different embeddings, and then you will plot using scatter plot library the different value. Here you see different example of kitten and cat, dog and puppy, and then completely something different lawn mower that is plot in different area. Good. Then let's do the same, but adopting a different approach, creating some question and answer. Here we're using the E5 model to do the embeddings, and here again we will plot the different text, the different question and answer into the vector, and then here you see the different plotting that has been applied into the vector, into the space nearly, because the one is, for example, about the summit definition request and the protein request that you have here in this example. Good. Then in the step 6, you calculate based on a particular query about the protein, you calculate the cousin distance of 5 different chunk of data that has been put into the vector. And then, of course, the cousin distance minor value will be your nearest result. Okay, then let's work using big text, in this case, an article. With this article, we will, let's say, explore different parts. In the step 7, we explore the limitation of the token size of a model. If you run, you will see that the model will not proceed because the text size will be truncated. Then in the step 8, we have a different visualization strategy of the chunking. Here you have the different definition, and then you are able to create different visualization adopting different strategy. The first one by chunking by recursive character without chunk overlapping. Then we have the same, but with chunk overlapping. You see here in the colors where the parts are overlapping. And then the last two examples are the splitting by token. And the same also with and without overlapping, and even using the retrieval surrounding chunk that has been explained into the theoretical part. Good. Here you can explore and play a bit with the parameter here to see how cool it's the strategy, and to find the right strategy on to set up the right parameter. Then let's using in the step 10 the an approach using purely ChatGPT. In this case, we provide a question, prompt question, using always the big text on top, and thanks to that, we are able to provide the answer that we provide. The same example in the step 11 is being done using Elastic itself, chunking the data, giving the data into an embedding model, place the model and calculate the cosine distance in this case in order to have a fast response, and then provide the response to the question. Good. Have fun to run through, and yes, if there are questions, please don't hesitate to ask.
Yeah, one of the we talk about regenerative retrieval augmented generation a lot in Elastic, and there's various reasons to do that. A lot of them Dave covered, and hallucinations and things like training cutoff date. So it's knowledge, it stops learning because these are not continuous models, continuously training models. Usually they are, you have a training cycle and then you stop and deploy them, especially the very large models. They take a long time and lots of money to train. So we can do things where, we can provide it fresh information or information that it hasn't been trained on. So, there's a couple examples there. Certainly information that's internal to an organization that just doesn't know about. You can provide that information. And what we're really doing in this case then is Elastic provides the answer, and it's in this list of documents or chunks somewhere. But we use the kind of amazing abilities of these generative models to quickly parse information, understand it, and then provide these really coherent answers back to the users in really helpful ways. So that way we can be kind of the intermediary and be a thing in there. So when we come to this, we have to then find the information for the users first. And so users load information into Elasticsearch or other search engines. We hope it's us, but we can then retrieve the information back, because that's the first part of RAG. And so there's different ways to do it. The first one we'll talk about is, BM25, text search, keyword search. So as you know, Elasticsearch is a search engine. We've been doing this since the mythical story of Shai wanting to create the recipe search engine. Not sure if that's really true or just mythology, or lore, but we'll see. We'll ask him next time. And the way we store information is in what we call the inverted index. And so you can see the examples here, but basically you can think of it as when you send documents into Elasticsearch, we parse out the information, and we can parse out little bits of it, or we can parse out the whole part. But in the example you see here, we parse out each individual word, and then we put it into an index. And it says this index has this word, it occurs this many times, and it's occurring in this document. So then when I search for, the choice is yours, and it's looking for, hitting on the word choice, for example, it immediately can go to that index, find the documents that are in it, and then quickly retrieve those documents back, and then score them and sort them and do all the stuff it does. But this is how we're able to, traverse terabytes of data in sub-second response times when we're scaled out, because we know we have directions on where to look. There's been improvements over the years, of course. There was TF-IDF, And then BM25 was an improvement on these things. But just to say that over the last decade plus, we've been continually improving and speeding up the relevancy and recall of text search. And, the way I think about text search versus semantic search, we'll get into in a minute, is, back when Google came out way back in the late 90s, around there, kind of had to play that keyword game where what are the website or what are the documents I wanted to come up with and to retrieve. And I had to think, like, what are the words that are probably in there? And if I didn't hit on those words, of course, there was like stemming and things like that. But if the words I chose weren't in that document or that website, I wasn't going to get good results. And so then you kind of play that iterative game of going back and forth. And today, then we have semantic search, which again, we'll get into in a second. But we want to be clear that while semantic search is very, very hot topic, it's something everyone talks about today, semantic search isn't the end all be all. It's not the only use case for search. BM25, lexical keyword search is definitely not dead. You can use them in combination, which we'll see in a little bit, but also things like if you're searching only on metadata that's specific, keyword tags, there's no reason really to use vector databases for that. BM25 can find those keywords extremely fast and be extremely good results. We can do things like date ranges. So I want to see all these documents, but within a certain date range, we can find that for you. I want to see all the restaurants that serve sausage pizza within, a quarter mile of where I am, that have more than 4-star reviews. These are all things that the traditional search engine can do extremely well and in combination or alone to go. So don't think that, traditional BM25 search is dead. And since we have been doing this for a while, we have an extensive, we call the DSL, query DSL library of pretty much if there's some kind of even off the wall corner search criteria you're trying to do, there's a good chance we have a search function that can find it. Might have to dig in the docs a little bit, but we can help with that. So with that said, we will move into the two areas of semantic search. First one we'll talk about is vector search. This is also, you'll start seeing it referred to as dense vector as compared to ELSER, which is sparse, which we'll get to in a minute. So searching on vectors in Elasticsearch, we saw earlier the HNSW algorithm that we used and how we're kind of going from that course map down and zooming into the map to find these documents quickly. We do that with KNN. So KNN is K, that's the number of candidates, and NN is approximate nearest neighbor. So approximate, because it is an approximation, it's still highly accurate, but you trade off a little bit of accuracy for a lot of speed. And you can see the query syntax on here. We again use KNN. We tell the field which contains the vector embeddings. And then you have the parameters, K, number of candidates, the similarity if you're trying to restrict it down to the, how close it is. The similarity is pretty interesting because this gets into that caching example Dave mentioned earlier. So because it's a nearest neighbor algorithm, if you have no neighbors that are, say close to what your input is, the algorithm is still going to go find the nearest neighbor. So even if all your little objects are over in this clump of space and I come up with a query up in the upper right, the nearest one's over here. Is it, semantically what I'm looking for? Maybe not. And so by having that similarity parameter, you can restrict down. This isn't something you always need to use, but if you're starting to get results that are kind of wonky, this is kind of like in traditional search where you have, no hits, similar kind of concept. And then when you're searching, you have to use in this case, a vector to search against vectors, because we're inserting a vector and we're using that to find the neighbors in the vector space. There's a couple ways to do this. The one way is if you're generating your vectors outside of Elasticsearch, you generate your vector and then you place it in the query. In that case, it would be where that query vector builder is. You just have the vector and you put your vector in. If you are using Elasticsearch, one of the benefits of hosting the embedding model with us is you can use this query vector builder. And what this says is, oh, hey, you're hosting the embedding model with Elastic. So you just provide the model name and then your model text. And what that'll do is you make one call to Elastic. Elastic says, oh, hang on, It makes an internal call to the embedding model, gets the vector back, puts it together, and then makes its search, and you get back the document. So it's a nice shortcut to do that, and you host it with us. Skip. And then further, building on all the tools we have, and Dave had that graph that had kind of a couple different circles and showed that we're not just a vector database, we still are a full search engine. And this is where these capabilities really come into play, because it's pretty uncommon that you're, at least in our use cases, that you're using a vector database and the only thing you care about are vectors. That's it. There are some research cases, obviously that's where you're doing it, but most often it's in combination with some other data. So for example, if I was searching for an image type, and I'm looking for similar images of a blue dog, for example, or I'm typing in blue dog and I'm using that with the clip model, and I have vector representations of a blue dog, I can do that, but I want to make sure that I get back the PNG format because that's what I have. So what it'll do is, it'll traverse the graph, but only consider candidates where the file type is PNG as opposed to JPEG or whatever. So you can restrict that down there. And that just makes it more effective results that you're getting back to your users. Couple other things in there. Source false. You don't need back all the whole source. You certainly don't need back all the vectors. And then field title. In this case, it would just return the title field, but maybe you want title and blob URL or something. The other thing is field collapsing. So a lot of times when you're especially doing chunking and you have multiple chunks of a document, but they all relate to one top level document. So if the Wikipedia article, for example, if you have the different chunks of it in different documents, but they all refer to, they're all part of one big long doc, it's fairly likely that if you're searching for something, fairly specific, that the top 3 documents you get back, the 3 passages that you hit, they're all for the same Wikipedia document. Now, I don't need back that same document 3 times. I just want back the one document and then the next 4 results. So what the collapse field does is it does just that. It takes the results that have the same value for field. So in this case, title enum, which is say title, and it'll say if they're all for the same title, it kind of collapses. Kind of think of it as running unique on the title, right? So you get back those. And what's nice is with the collapse, it not only collapses those together, but again, if I had 5 results and the top 3 were all from the same document and those collapse into one, I'll still get back five documents. It still kind of keeps rolling up until it fills out that, in this case, 5 result bucket. So a lot of ways you can structure your data in Elastic and as the vector data store. So as of 8.11, you can store multiple passages in one document in the nested vector. So what this does is, again, that Wikipedia article that's, let's say, 10 chunks long, we break it into 10 passages. You have the option to store 10 separate documents, maybe with the title, and each of those 10 documents has the passage and the vector for that passage, but then it also has the full Wikipedia article. And so then if I got those back, I'm duplicating that full Wikipedia article in the Elastic Store 10 times. Another way you could do it after 8.11 is store the passages all together in one document. So I have a passages nested field, and then all my passages are in that nested field. And then I also have, the Wikipedia article once and the title. So one document contains the title, the original full document in text, and then each individual passage. And this way you kind of keep everything together. You can do things like inner hits to only return the passage that it hits on, but still get back the document that way. There's trade-offs for this. Nested isn't always the fastest, but depends on your use case. But it just kind of gives you that flexibility to do that. One thing to keep in mind, especially with dense vector search, is it's pretty kind of corner case when you're estimating or ballparking. And most search use cases, obviously there's consideration on CPU requirements, how many users are querying at one time, how big are the documents coming back. And then sometimes some caching considerations, but oftentimes let's say the increment of growth isn't usually around RAM. I mean, sometimes it is, but generally we look at the compute to do all this because we're searching the inverted index, and we can do that pretty fast. Now, for KNN, dense vector search, and elastic to be performant, we need to be able to cache all the vectors into the off-heap RAM on the data nodes. This is somewhat, again, unique for this in that if we don't fit, or have the ability to cache all the data on the vectors in the data node, vector search will still work, but it will oftentimes be significantly slower because, again, we have that graph we have to traverse. Instead of being able to run through it quickly in RAM, the search threads have to then pull from disk and read, and that slows it down a lot. We do have ballpark estimators and calculators we can help do this, but you can see kind of the basic calculation here. It's 4 times number of dimensions plus 12 times the number of vectors. Number of vectors there is if I have 1,000 documents and each document has 1 vector field, that's 1,000. If I have 1,000 documents and each vector has 10 vector fields, be it nested or not, that's 10,000. So keep in mind what that means, and also keep in mind replicas add a whole multiplication to it. Now, as you can kind of potentially guess, and number of dimensions is the number of dimensions that the embedding model produces. All the embedding models have a specific number of dimensions they kick out. These are the slots that all the coordinates fit into. 512, 768, 1536 are the common ones. There's lots of others. So as you can kind of quickly do some math in your head, hundreds of millions of vectors, that's a lot of RAM. And of course, it's the high performant RAM because we want to search fast. That's pricey. So what we introduced in A12 is the ability to auto quantize. So quantization has been around for a while. We certainly didn't invent it, but it was something you had to do on your own outside the stack. And there's some blog articles that go into really great detail on this, but essentially you're converting a float 32 vector into an int 8. So it reduces, at the end of the day, the size requirements down to by about 75%. Something in the chat, but I'm not really watching the chat, Dave.
I got it. You're cool.
Okay. So you trade off potentially a little bit of accuracy again for this reduction in size. Our ML engineers have done plenty of testing, as have other people outside of the organization, just in vector research realms. Generally, it's fairly acceptable, but obviously that's something you and your users have to evaluate. But the trade-off is definitely significant, and so you're able to fit many more vectors into your use case. And again, as of A12, we do this automatically. You change like 2 mapping parameters in the mapping of the index, and we automatically quantize on index and do it. So it's really a great feature we have. It's exciting. And we do currently support 4096 dimensions. I personally haven't seen anyone try to push that, but I'm sure there's someone out there doing it. And then the similarity types that we expect are, or that the model expects that we support, are L2 norm, dot product, and cosine, just little different ways of calculating the similarity. Oops. Get back. Okay. Yeah, and this is a quick example of the dense vector mapping, and where you have the type is dense vector, the dimensions is 768, index is true, talk about that in a sec, and then similarity is the dot product. As of A12, there's 2 things I'd like to point out. One is that we now automatically normalize and use dot product. If you put cosine in there, we're going to normalize it and use dot product for cosine anyways. And the other thing is, if you have over, I forgot the number, I want to say like 100 dimensions, we're going to automatically detect, on first index that that's a dense vector field. So if you don't put in the number of dimensions or similarity, we'll automatically put that in. But as is best case for productionalizing a environment, you want to make sure you're mapping your index correctly to what you expect. but just if you're testing something, kind of shortcut that. The index true is tells Elasticsearch to create that HNSW graph behind the scenes as part of the index so that you can run KNN search. If you set it to false, we'll still index the vectors, of course, but they'll just be floats. So then, or an array. So then you can't run KNN, but you can still use it for script score. So if you're using it for, a rescore phase or something, or some other use case where you just need access to these numbers, essentially, you can store them in there, and you just can't run KNN search. But as shown here, you can store multiple, you can have different fields within a document, use different models. So you can have one document, that has the title, use, in this case, the Distill Roberta model, which is trained on sentence pairings, and then have the body trained on MS Marco Mini LM. That's more effective for, the body of text because it's based on search queries. So you just have to keep track of those for now. But yeah, lots of flexibility to do what you want. This script score is where I was talking, if you're not going to be using KNN, one use case is using it for script score. There's a couple of different ways to do this, use cases rather, for script score. This one in particular is using the vectors for as like a personalization rescore. The idea behind this is if you or users, created a model, trained up a model based on, let's say, you're a shopping company and you have customers buy different items, have different spending ranges, different products, different types, they live different places, all these kind of things that you use to categorize users. You could create a vector representation of the user, and maybe you update it every day or whatever, but you have this index of user vectors. And so, if there's one of me, when Jeff logs into your site and I search for whatever that costs more than $1,000, instead of just having the default score or scoring of documents, maybe we'll use my vector representation to find similar or likely documents or products, I guess, that I'm likely to buy. So gives a little bit of flexibility. That's definitely like an advanced use case, but it's in there should it come up. And yeah, so there's a lot. Any question you need me to answer in the chat, Dave, or you got it? I just see it.
We're good. We're debating the pros and cons and like how to learn where Elasticsearch will have trouble with the nested vector pattern where you have like multiple passages all in one document with all the vectors. Because we know that there's a cap, right? There's the RAM issues of Lucene is flat, so having deeply nested structures, eventually runs into problems, and how to know ahead of time where that problem is going to show up and how difficult that is to figure out.
Yeah, I agree. We have like nightly bench rally tracks rather for the benchmarking site. We our perf team does that do there's like three, or I think there's at least three of dense vector. I'd like to see them add in a nested track because it's a great point. Everyone's like, I'm tentatively excited, but yeah, I don't know where the limit is on. Is it 2? Is it 5? 50?
Yeah. I've got a question on where can people learn more about like the personalization vector bit, right?
I'm not sure if we have any particular articles. And honestly, I'm not sure if Hildebrand came up with that example or not. I just kind of know the general idea behind it. And I've seen it brought up before where you can create, vectors to represent a user, but it's a good question. We should find an example.
So we have customers that have been using the rank features feature of Lucene for 10 years to do this, right? So it's not a new thing. We're just sort of like, well, now we got an actual dense vector. Well, here's how you would do the same thing. But we're sort of knowing that some of our customers have done the data science work to build their own personalization embeddings. And so in a way, it's like, oh, let me find the open source version for it. Uh-oh. There are some things you get into like image recognition and specific other things where the best is commercial, unfortunately, right? Because it's just worth too much money.
Yep, for sure. Cool. All right. So we will move on to ELSER, the Elastic Learn Sparse Encoder. The R is at the end. So what is the Elastic Learn Sparse Encoder? So it is a out-of-the-box relevance model that is, out of domain, out of, the box in general. And the idea behind it essentially is, sorry, I'm seeing all these slides. What this chart is showing is if you have a model that's, a BERT model or whatever, and you fine tune it for a specific use case. I know that the use case, the kind of different data sets are the yellow across the top. Those are different types of data sets. If you fine tune it for one of those use cases and then you query against that use case, let's say you have medical data and it has medical jargon and all the research, and then you're searching and querying and doing vector search for medical type queries, it's going to perform really well. But if you have, that medical fine-tuned model and it's querying against then, let's say, newspaper articles that are completely or financial documents, maybe something unrelated, the performance is going to drop off because it's not trained for that type of model. And then so you can see the search rankings across there. So BM25 is the just general text search. RRF, we haven't talked about that yet. That's combining BM25 and multiple types of searches, really. So it's hybrid search. Automatically, linear search is doing it linearly, where you kind of just set your hard code numbers. SPLADE is the sparse vector research paper and model that kind of kicked off this sparse vector. We'll talk about the difference between that and dense in a second. And then the Elastic Learn Sparse Encoder is ELSER, and the last one is BM25 and ELSER together. So you can study this chart all day. What it essentially is, the Elastic Learn Sparse Encoder is designed to be this out-of-domain object or model. So we have a lot of our customers who just have regular text that you or I could read. It's not any kind of weird industry jargon. It's, if you gave me some documents, I could read it and understand it, essentially. And so that's what the ELSER model kind of gets to them. It's designed to be a nice general text. So if you have English text, ELSER should perform well on it, and you should definitely review it across. And it generalizes, you can see, across domains without training. So what's a sparse vector as opposed to a dense vector? So a dense vector is called dense because we mentioned the dimensions of a model. So let's say 768 dimensions. If you look at the array, you kind of think of each one of those 768, array points is like slots to fill. If a model is 768 dimensional dense vector model, it will always fill up every slot with a number. Doesn't matter. Now, what a sparse vector, on the other hand, does is it has its entire library, which I meant to look this up. I can't remember if it's like 100,000 or be off by a dimension there, exponents, but it's an extremely large dimensional library. But when it writes out its numbers, most of those are zeros because it's sparse. And when you send in a string of text, not everything, these models have their internal library, and that's what all these, huge key maps are. I'm only going to hit on a handful of them, because my sentence doesn't make sense to any of these other keywords it has, but I still write out, so potentially I can write out all these values, and most of them are zero. So the way it kind of manifests, and you can see it when we write out the data in Elasticsearch, is instead of outputting numbers, which are coordinates in a vector space, it writes out tokens and then a score. And which you can see here in the tokens field. Now, I caution people to not try to interpret too much the results, the individual tokens, that are in there. Yes, many of them are words that, I know what muscular and practice and rehab mean, but to the model, they're tokens, and they might not always, I've seen people get into trouble basically trying to read the 25 tokens or 50 tokens that it kicks out, and some of them seem like nonsense. But when you run a query against it, it makes sense. So just think of them as tokens, accept them as they are, and instead of trying to evaluate what the individual word list is, do the normal evaluation do the results that we use with the model, are they, highly relevant? And that's how
Yeah.
you should evaluate this model.
Never build a search app where you show these token names to the user because they may not be politically correct.
I've been arguing that we should not even, they could put a key number, right? Like the index number could, or an ID number rather, could be in there. But
Yeah. So, there may be some unintended interpretation of bias from the tokens that it happened to pick out as being a good word to be the center point between a whole bunch of different concepts found in the training data. And people might get upset if they're
Yes.
like, I didn't say that. Why does this thing think I'm a bad person? Right.
Yeah. So that's a whole fun thing. The other thing, one of the big advantages, besides being a nice, it's a model the Elastic trains, the engineers train, we're refining it. We can install it with a one-click install in Elastic. You post it, you click the button, it downloads. You don't have to do anything really other than click the button and have an ML node. But the big advantage, easy out-of-domain relevance. But the other one that's really nice is, I talked about that expensive RAM requirement for dense vector. The ELSR and sparse vectors do not have that requirement because they are, words and numbers ultimately that it's storing. It stores it back in the inverted index. So we don't have that high RAM requirement. Of course, so we're back really to like a normal search use case of what's my normal compute and resource requirements. We don't have this kind of weird, what's my crazy RAM requirement. It's inverted index. It's nice and easy. So let me jump here for a sec. Yeah, you can use just like cover this in dense vectors. You can use the ingest pipeline to inference the text you're running through ELSR. Again, you use the field map to tell what's the text to the text field. The model is always .ELSR _ model _ check the version. We released version 2, so just go in the train model API or the UI and you grab the model. And then, you tell where you want to store the data. And then, of course, if it catches a doc that's different, throw that on there. But you can store, do this all in ingest. Sorry, I was looking for one thing. One thing I wanted to mention too, it's kind of around the don't show your users the tokens. For both dense vector and sparse vector data, you can exclude those values from source in the mapping. That's a good practice. It'll save on size because it doesn't have to store, either all these numbers for the dense vector, or it doesn't have to store all these extra tokens. ELSR still has a percentage increase on storing it because even it's still storing it, but we're just not wasting storing it in source. So you're still obviously able to store it, but definitely look at excluding it from source and when you're doing. Oh, sorry. So then when you're querying, it's pretty similar to a KNN search. It's a little more simplified, really. You give it again in this case a text expansion query type, and you give it the field that contains the tokens, and the model ID again is ELSR, whichever specific version, and then the model text. And just like the query vector builder, you send that search API in, makes the call internally to ELSR, gets back the expanded tokens, and then runs its search and get back the fields that you specify. So fusing all these fun search technologies we have together, we have reciprocal rank fusion. Now you can, I'm sorry, I jumped around. It's the beta. You can combine scoring linearly, meaning if you had a really specific use case and you really knew the rankings that could only come out, you can just kind of provide a weight to KNN versus query, or KNN, whichever your query typed. That's really hard, and you generally, it's kind of hard to know the scoring. The idea behind reciprocal rank fusion is, the way the scoring range that a KNN query results comes back is generally between 0 and 1, but a BM25 query could be 0 to, whatever, really high number. And so those scoring ranges are completely different, and just kind of sorting them by the score, KNN, dense vector search, is almost always going to be at the bottom, and you don't get good results at all. So reciprocal rank fusion, and we have a docs around to explain this, essentially tries to automatically take these two disparate scoring methodologies. It takes the order that the documents are returned in, individually. There's a little bit of a constant score and then a weight, but based on the position they're in, essentially, if they're high in both, it goes high together. If they're high in one, it kind of puts them together. It's pretty straightforward little formula. And again, if you look in there, but at the end of the day, you just turn on RF, and then these two unrelated scoring ranges come together automatically. So you can see, the rank 1 and rank 2, you kind of ignore this, you throw out the scores, you let RF do its thing, and you have your new sorted combined hybrid query results. As meant, the little asterisks at the bottom, the engineering team is working on some changes to the DSL and retrievers in general. However, RRF is not something we invented. So RRF essentially won't change. It's just more of a syntax change, and under the hood there might be a little bit of optimization. But if your users are saying, well, it's not GA, I'm hesitant to use it, my advice to people is definitely test it out. At the least test it out to see if RRF works for you. If it does, and you still want to wait, worst case, that it works, you're just waiting for the new API to come out. It's there. So what we're going to do is run through create a RAG application, or run the one that's been created. As a review, what we're doing is using this RAG UI we have, where we'll ask questions. It's going to use Elasticsearch to retrieve relevant documents, in this case from Wikipedia, and then augment our search and send it off to an LLM, in this case, Azure's OpenAI, and then return that answer to us. So we'll do a couple things. There's a couple different options on how you do it. We'll show it in a second. My one kind of caveat here, since this is the beta, and Dave mentioned this. When I first loaded Wikipedia, it worked, but then Dave found out that it had large random gaps in the data. So when you're searching for something, if you consistently get no answers on that one question, maybe change topics. I'm loading the full one, but I'm trying not to charge, Elastic $1 million to blast this in. So just note that. I know Batman works. So let's hop over to the lab. Oops. So here's the lab. I guess I'll make my screen bigger too. All right, so I reset mine. Also, since this is new, I'll run this first one. We'll do the first two cells and then hang on a second. So I'll run the first cell. This is just like the other ones. We're loading some of the environment variables and some other stuff. Again, the magic code for today is wheat trial. Should come in a second. Okay, so throw that in there. Wheat trial. We're gonna load that. Cool. Since we have a RAG app, it's a web UI, we'll try to make it a little nice. The library we're using is Streamlit. If you're not familiar with Streamlit, it's a Python library. It's designed really to be a quick prototyping tool for, originally like ML data science. I kind of got picked up by the GenAI crew. It's nice in that it's very easy to build these UI components that work really well, but it's not something that's so, beautiful you're going to throw on, multi-billion dollar website, right? But still, we want to make it look a little nice. So we're going to download a couple images. And then this is the part that's not in your code. I'll put it in chat. Let me check. Sorry. Again, if you don't do this, it's not a big deal. Put it before all the pip installs. The only thing this does is it's going to force your your Streamlit app to be in dark mode, which will make the background you'll see is all dark. So if the components are dark, it works better. If not, it's totally not a big deal. But it's going to install this dot, kind of refresh the folder list on the left. You'll now see some images and you'll see this dot Streamlit config. After the course, I'll push it to main thing. Okay, anyways, we're going to run some installers. So we're running the tick token, count tokens. I don't know if we actually need Cohere, but I don't think we do. But anyways, OpenAI, because we're going to use Azure's OpenAI.
You needed to avoid a warning for the tokenizer for some reason.
All right. Well, that's good. That's interesting. Some other libraries, Streamlit, Elasticsearch, obviously, Elastic APM, so we can watch what you're doing later. And again, other stuff, LLM cache. Local Tunnel is this fun library. So since we're running in Google's generously donated free environment, it is in Google. And the way Streamlit works, generally, most people use it running on their laptops for, again, prototyping and stuff. And it launches a local host, and you're off and running because you're you have the port open on the web. Google locks it down, understandably, so we had to find a way to punch a hole in it in their network. Local Tunnel is this library that does just that. It sets up an IP and connects a tunnel through the network. I think Cloudflare bought it a year or two ago at some point. I just pointed out because later on you'll see it's going to generate a random subdomain. And well, full URL, but subdomain is random. I've never seen anything that's gotten us in trouble, but there's some wonky things. We didn't make it up. We'll get to that, but it's just coming up. Okay, last loading. We should be all loaded. So the first, we're going to do two kind of real short little labs to kind of explain what's happening behind the scenes, and then we'll run the actual Streamlit app. So the first one, each one of these two, lab 4.1 and 4.2, we have a setup block and then the actual things. So I'm not going to go through all the lines of code because we kind of did in the labs, and you're feel free to go through it later. But really, we're just setting up the query. We're going to run what documents we want to get back and then make it kind of. But this is using the same Elasticsearch index that has that mostly intact Wikipedia index. And so the question I'll ask is, who is Batman? That's my question. And then to run it, we're just going to run, in this case, the hybrid search, which again is up at the top. If I run that, it takes a second. And what we're doing is we're getting back in this case, 5 documents. So we're hitting the top 5 results for this hybrid of KNN and 25 search. So the 5, results, and you could argue this might need some tuning, but this is where the top 5 results that came back. So these are the 5 results that, the user queries we've gotten from Elastic. And these are the documents that we're going to use then to augment the, call to the LLM, the generative model. So the second part is sending these documents with the prompt for the RAG response. So again, we can run that. This is a pretty short, very short prompt just for the sake of the lab. Again, you're a helpful assistant who answers query from Wikipedia. The way we're building up this prompt is, and this is something you all do in the code, and you kind of only expose that question box to your users, is you say, the instructions are answer the following question, and then we'll replace the question, in this case, who is Batman? Using only Wikipedia passages provided. If the answer is not provided in the passage, respond only with I'm unable to answer the user's question. Now, these last 2 lines of the prompt are important. This is our best attempt, short prompt anyways, to minimize hallucinations. So it tells the generative model, if the data we send you, if the documents we send you don't contain the answer, don't go ahead and generate an answer. Don't make something up. Don't use your own kind of generative knowledge. Just say this specific phrase so that you're out. If you're writing this in a more, real world environment, you can have it return, JSON or an HTTP error code, right? And you look for that actual code. But you might see this phrase when you're testing out in the lab in a minute. If you get back this answer or something like this, that's the LLM telling you the data we sent from Elastic didn't have the answer. So we ran that, And then, so here we're going to, again, the user's question, which we did before, who is Batman? And the AI response in this case is superhero pairing in comic books. So what we did was we took those 5 documents and we sent them to, yes, it's recorded. Yeah, it's recorded. We sent that to Elastic using, or to OpenAI, Azure's OpenAI for the prompt. So, okay, get into the fun UI. So we have this application. It's the RAG application. And if you run this, the way we have to do this in, since we're using Jupyter Notebook, is we use this little fancy feature in Colab in Jupyter rather, to say, write out this file, write out all this code to app.py. So it takes all the code in this cell and writes it out. Again, if I refresh, we now have a file on the left side that says app.py. Cool. This is where normally if you're running it on your laptop or something, you have the file sitting on your directory. Now, there's a lot going on here, and I'm not going to read through all this because it's long. Most of it's just code that is either querying Elastic, or a lot of it's just functions parsing out data, making Streamlit look, somewhat nice and things like that. But you see writing out app.py, and then the show runner here is we run Streamlit, and this is where you're going to get, tired cruise dress. I've seen crazier stuff. What you have to do is grab that IP address, click on the URL. It's going to pop open a new window. This is a little kind of gate to make sure bots aren't using this. But you paste in that IP address that was provided. Yours is going to be different. Click submit. And if all goes well, we have our Wikipedia demo platform. So make this a little bigger. Okay. So you feel free to test this out and play with it. Again, keep in mind, you might find gaps in the data. There's a couple of features of this I'll kind of run through real quick before using it. So there's 2 dropdowns. Obviously the simplest way is just type in who is Batman. I had find my answer. We'll see if it works. So this is an interesting one, and I'll show you why I did this in a second. So we can customize the prompt template. If you find any errors in here, let me know. I'm still kind of debugging that. We're not really going to use that today. The more interesting side for today's use case is this retrieval, search, and display options. So it's kind of a bunch of stuff going on here. It's in 3 main sections. The first one is retrieval options. So you can do semantic search, which in this case is using KNN search. You can use lexical search, which is BM25. And then the augment method is, do I want to send the full Wikipedia text as part of the prompt, which Dave's example earlier showed that could use a lot of tokens, or do I want to just send in the passages that get hit? The way we chunked this up was around 500 tokens with 50 token overlap. So there's some context in there and a little bit of overlap context, but you'll have to have trial and error. You can use hybrid search. If you have semantic search turned on, you can use hybrid search, which will add in BM25. And then the number of chunks, so 1 to 5 chunks are documents in this case. So if I move this up to 5, for example, let's see, does it? It's you'll see the little running person up there. So what's interesting is when I moved it to 5 documents, I actually got a response. And this is where, giving the LLM as much information as you think you need, depending on your data set, is important. Sometimes sending in just one chunk of text might work. Again, this data set and this queries could be probably tuned a little better to dial in. But oftentimes, if you give back a couple documents to the LLM, you're going to get better results. And so then down here, we have display options. This is just kind of making stuff easier as you play around. You'll see all the augmented chunks that are going to be sent in. You'll see the actual Elasticsearch response. This is all kind of like with debug turned on, you can kind of think of it. A lot of times when I started testing, I kept closing those, and then I realized maybe I just want to turn them off because I don't need to see it the 20th time. But you'll see what are the search settings. So I have semantic search turned on. I have how many documents or chunks, depending on my selection. Again, the other 2 settings in there. And then at the bottom, what you'll see, which is kind of, I know it's at the bottom, I might move it up because it's kind of the highlight of the show here, is that Elasticsearch took 0.19 seconds to run, semantic search across, I think it's, I don't remember the doc count. The raw docs was like 180 gigs. Found 5 documents. And then the generative answer took 3.4 seconds to come back. That's actually not bad for generative answer. I think maybe they're getting better or their responses or something, because it was taking like, sorry, am I saying Elastic Docs? I've been doing this demo for so long. Thanks, Nicole. It used to be Elastic Docs. It's Wikipedia. Sorry. I did it so many times. It used to be Wikipedia. Yeah, it's Wikipedia. Thank you. I'll have to hit myself and slap my hand every time I say it. It searches the Wikipedia docs and returns those chunks. So again, if you want to turn on things like use hybrid search, you can return the matching chunk and see what happens. The other thing in here, you get kind of interesting results when you change some of these settings around. The other thing is the caching option then. So this was that example where when let's see if I find an answer. So what this is doing is, there's some information on the side. If you turn on the caching, we query the Elasticsearch cache index first. If there's nothing in there, it goes on its normal RAG routine, gets some documents back from Elastic, passes them to the LLM, and then you get back your answer. But we also then say, again, maybe this is Wikipedia. People are probably going to ask the same questions, or it's a knowledge base and people are going to ask the same questions. So we store the original user question, so who is Batman, and we vectorize that question and store the vector, but we also store the text that the generative model returned. So whatever it returned, we store that in just a regular text field. So then on the next time when I ask who is Batman or it's Batman, let's see, it returns, oh, there's a hit, and there is, we're gonna just return that because we already generated the answer. This is nice. And the example we do is like, I'm a professional multi-billion-dollar company. I want to make sure the answers that we're returning are, not something insane. So I could sit down and have my team spend an hour, a couple hours, a couple days churning through hundreds of most common questions that we already know because we use Elastic APM. And I go through those, I vet the answers, and I put them in cache. So then when users ask questions, we hit the cache. But to control that similarity parameter, which we talked about, that's what I'm attempting to show here. So who was Batman is pretty close to who is Batman. I think the W, when I did it originally, was lowercase, for example. So it's, it calculates the score, 0.972, right? And so you can go in here and slide this value, and let's say I'm going to make it this. So 0.98. What that says is my similarity value has to now be calculated to be 0.98. And if it's further away than that, we're going to see on the side cache miss, and it makes the normal RAG call. This is where then you can allow your users to say, again, because KNN search is nearest neighbor, it doesn't really care if it's the best, like if it's a good answer, it's what's really the nearest document or point in its space. So this allows you to kind of control that down. Yeah. So again, feel free to play around with this. You can turn on the full prompt response and let go.
So part 5, just thinking about costs, thinking about monitoring. So the thing you need to know about using large language models is that usually the cost revolves around the token. If I'm using a third-party service, right, I really am charged by the tokens. They count them. They show up in my bill. You can see them in the JSON response. But even if I'm self-hosting, right, the amount of tokens I send the model is going to have a lot to do with the number of clock cycles on that GPU that I'm going to be consuming, and as a result, the amount of concurrency that I can have and the overall GPU cost, even if I'm running those GPUs all the time, right? So GPU cost, token cost, very, very similar, right? And sometimes these models, when you go to their websites, they charge you different amounts for the prompt versus the response versus like context tokens. Like they can have a little bit of nuance there. what is a token? A token is about 4 characters, right? It's a portion of a word. So you can think 100 tokens is about 75 words. You want to learn how much your text costs in tokens, right? There's little code samples you can do it. You can even ask ChatGPT to write the Python code to count the tokens for you. Or you can go to the OpenAI tokenizer tool. Stop there and say that I know that there are members of the public sector services team. Do not take your customers' data and just punch it into a web tool. You have now spilled it to OpenAI, and who knows what they do with it. So just think about it before putting in private data into a cloud-hosted tokenizer. Obviously, doing it yourself in the correct environment on the correct network is pretty much risk-free. All right. So looking at the cost tables, we can see some things, right? The biggest model that you can buy from ChatGPT costs about 6 cents per 1,000 tokens, right? And we had some prompts in there where there were like 3,000 tokens, so that would cost us a portion of $1 there, right? Almost more than 2 bits. So GPT-4, the big model, costs more than the one that has a smaller context window, right? And that pretty much plays out for some of its competitors as well, right? So you can go and estimate the cost of what is it going to take to operate an AI app by looking at simple calculator. How many requests are there per day, and then the prompts that I'm putting in. About how many tokens are they, and the response they come back. How many tokens are they? And thinking about, well, if I can get the app to work on ChatGPT 3.5, I might have more than a 10x difference between that versus just using the biggest model. Right? So don't default necessarily to the biggest model, maybe in dev or something. But if you can get away with using one of the smaller ones, especially stuff for like RAG, where we're not like depending on extreme logic, you might have a different LLM choice per like little microservice or per agent in your prompt flow or in your Lang chain kind of chain of prompts. Right? You don't have to think it all has to get done with one. Another thing to think about is that not models are good at different things and they cost different amounts. So there've been some fun research papers about, trying it on a cheap model first, using reflection to ask, was this the right answer? And if it's not, then using the most expensive model. And then overall, kind of optimizing the cost versus quality of answer with that mechanism. But in that, you get some interesting stats. Like here, we see that a more expensive model like J1, right, actually got worse results than ChatGPT. And that's GPT-3 over there, with GPT-4 being used as the baseline. And that was on commodity news headlines data. But doing a reading comprehension data test, J1 was only slightly more expensive, but grossly outperformed ChatGPT. Right, so you're going to want to go and look at your data, try it with different models, and see what's best. Right, there's not a one size fits all. Yes, GPT-4 is currently like the kind of leading the pack in a lot of different metrics, but not necessarily the cost metric. Right, so just kind of getting in there and figuring that out. All right. Another thing to think about is like, how are you monitoring your costs, right? Well, Elastic Observability has all kinds of different ways of grabbing that data, whether it's looking at people using the AI app that you build with real user monitoring by instrumenting the actual web or mobile client, or in your application and middle tier, using synthetic tests to make sure that it's still on, using log aggregation to grab out all the logs from the various systems, getting the application performance monitoring, and even grabbing network telemetry, right? If you have the ability to kind of have your own little man in the middle attack and pull open those JSON packets that are going through the network, right? If you have an enterprise network setup where inside your intranet you're able to decrypt packets and run them through a Zeek filter or something like that and grab out the token costs, you will be able to get a very accurate number on the token costs, regardless of whether or not the person's using the large language model service through the actual approved app, right? Maybe a good way to spot people using ChatGPT in ways that aren't approved by the enterprise. So lots of fun stuff you can do here, but pulling it all together, we have the ability to kind of aggregate and create a complete picture of this app, which will help us run a better service, have more reliability, and maybe understand, are our users having a good experience? What can we do in the next version so that they have a better experience? If you don't monitor it, you can't improve it. right? So we were able to monitor it in wave 1 of this workshop and see, wow, a lot of the customers are getting the I can't answer that question response. Maybe we should tweak this so that more of them have a fun Batman answer early on, right? All right. So looking at it, let's just jump over into APM. So if I pull open, where's an APM view here? If I pull open what you folks are doing on the proxy right now and pull open the service map, here it is. There's your lab, right? Which I think we need to change the name on to lab 4, right? Here's the lab, and it's hitting Elasticsearch for the vector search, and it's hitting the LLM proxy, which we've deployed in a run container. That proxy is also pulling out its own telemetry, and distributed tracing is being used to kind of like walk the path of that experience all the way through. And we're load balancing across 3 different URLs. This one actually, is, I believe, is a couple of different data centers. And then we got a Japanese data center, a French data center, I believe a German data center in there. Right. So we're load balancing your queries across the world just in case one of these gets busy. I can see my logs, I can see my errors, and I can see all that. We've also built a dashboard of the costs. Before I get into that, where's my slide? Here we are, right? In summary, right, we've looked at all this. We're monitoring the logs. We're monitoring all the tokens, kind of playing. We've had a chance to talk about LLM cache, shown diagrams of a couple of other things, but we've learned a lot, right? We sort of, at this point, it's late in the day for me. You're probably pretty brain tired. So we'll just end with a little test, a little question for everybody, which is, we were just utilizing the proxy to go look at, and you know, while there were some caching layers in there, right? How much money do you think we just spent? Uncle Shy just paid for us to use ChatGPT for 3 hours. I don't know how many of you were left in the room. I'd have to look at the participants tab, which is there's 19 of you left in the room. We started with 29. How much money do you think we spent? So throw it out. Sherry's run this workshop, so maybe vote on something close to Sherry. But how much money? $1,000, buck? We don't know, because this workshop has never been run with more than one person running at a time. This is the first run of this particular model, and I wouldn't be too surprised if the actual dashboard for it is broken. So I'll pull it open here. First of all, we know that 16 people started lab 1 and 2, 12 got to lab 3, and 13 got to lab 4. So somebody came back from the bathroom, right, or joined late or something. We know these are the Google data centers their collabs were running out of. We can't trace it back to their home. And we can see the moment, this is when they actually went and pulled the env file. Isn't that cool? I built that. Isn't that cool? If I go to the actual LLM cost dashboard, I think it's broken, and we're going to have to look into why. But you would learn that this probably cost us all of 20 cents. If I go into discover in the workshop, right, and say only when the total costs like exists, and add that filter and get it down there and say, let's just pull out the cost, the total cost, total cost, right, and get the tokens. We can get the tokens that are coming out of here, portions of a cent, right, that are enriched by the data, but something probably broke in the ingest pipeline because we've never actually run it against this version of the code. So I can't get you the actual one, but when you run this for a customer, what actually happens is we'll show them the dashboard, and it'll show kind of full visibility about that, as well as being able to see their queries, reminding people that you better know who's logging your queries and logging your data and monitoring all that stuff, because it has your customers' questions and it might be sensitive. All right. So call to action. We're always putting new stuff up in Elastic.co Search Labs, right? This is where we kind of put all the latest and greatest in code samples in a GitHub repo full of like little bite-sized pieces of, hey, try this, hey, try this. Great thing to send customers. And we've been going for 3 hours. So I'm going to ask one more thing of you, knowing we're sort of all tired. You know, where we've had this great experience, we've had this wonderful workshop that's happened. But if you could do one last thing, which is go into your Google Calendar, the invite, there's a link to a feedback survey. And before it's out of your head, just give us a couple of notes in the last couple of minutes here, and let us know, what would you change, what worked well, how'd it go, What are the questions we thought of a week ago when we made that survey? Please fill them out and let us know how it went, because we've sort of got a chance here to work out any rough edges before putting it in front of a lot of customers globally. So we'd really appreciate it. Juan, thank you for inviting your team and getting this going. I know we've been talking about maybe running it for your team since the beginning of Wave 1, so I'm glad we got it in. Good to know kind of people want to do this type of stuff as teams. Thanks, everybody. We will be posting this recording at some point. Well, I'll post it back to anybody that was on the invite list, and it'll probably, for a little while here, be the official recording for those that are studying. So thanks, everybody. Thanks, Jeff.
Thank you.
Bringing the knowledge.
Dave pushed this thing through. I didn't think it was going to get done by January 31st. Let me tell you. Got it done.
I wasn't worried in the slightest, Jeff.
That's right. Neither was I when I was sitting on my couch coding.
All right. Thanks, everybody.
Thanks.